Hello class, my name is Christopher, and I did my project on several of the Project Euler problems, and today I'm going to share with you my implementation of problem 273. I'm choosing to share 273 specifically for a handful of reasons. For one, there's nothing in this problem that is beyond the scope of simple algebra, and I think it's relatively simple to wrap your head around even if you don't see how to get to the solution. Secondly, I coded my implementation of this problem in Java, and Java is an object-oriented programming language. If you don't know what that means, that's fine, and we'll get into later why I think an object-oriented programming language is very suitable for this problem. Not necessary, but preferable in my case. Third, I think this problem is a beautiful example of how, when working with lots of really large numbers, discovering some simple formula and algorithm can drastically reduce the complexity of the problem. We'll get into all of that later. For now, I'm just going to break down the problem. Consider the following equation: a squared plus b squared equals n. Many times I'm going to say that n is the sum of two squares because a and b are both squares. I'm also going to add some restrictions on these values. B must be greater than A, and they're both positive. And all three values, A, B, and N, must all be integers. So, pick any value of N, and the equation A squared plus B squared equals N may have solutions, it might not, and it could have many solutions. Let's look at some examples. For the case when n equals 5, there is only one solution. Let a equal 1, let b equal 2, and the sum of their squares equals 5. However, when n equals 65, we actually have two distinct solutions. Let a equal 1 and b equal 8, or let a equal 4 and b equal 7. In either way, the sum of their squares will be 65. However, if we let n equal 11, there are no solutions to this equation. You can try any value of a and b that you will want, and you will find that there are no cases where 11 can be represented as the sum of two squares. Now that we've looked at a couple examples, I'm going to define a function. I'm going to define the function s of n. Whenever you see s of n, think sum, s, sum. And s of n is going to be the sum of the values of a that solve the equation a squared plus b squared equals n. Let's break down what that means. So since when n equals 5, there's only one possible solution, the sum of all of a in this solution is just a equals 1. That's why s of 5 equals 1. However, s of 65, there were two distinct solutions to this equation. So we choose both a values, sum them together, and we get s of 65 equals 5. I think it logically follows that s of 11 therefore equals 0 because there were no solutions and there are no a values to sum. So here is the objective that problem 273 tasks us with. Calculate the sum of all s of n for all square-free n, where n is only divisible by prime numbers that are less than 150, and take the form 4k plus 1, where k is some integer. Now that's a lot to take in, so let's break down some parts. What does it mean for a number to be square-free? Well, a square-free number means that when you factorize it down to just its prime factors, none of its prime factors should appear more than once. So for example, 14's prime factorization is 2 and 7. Since neither 2 or 7 appear multiple times in that prime factorization, 14 is a square-free number. However, 28 is not a square-free number because its prime factorization is 2 times 2 times 7. Since the 2 appears twice, it is not square-free. This condition limits how many n we can have. Let's also consider these primes. At the bottom, I have listed all of the primes that take this form of 4k plus 1, which simply means that the prime number is exactly one more than a multiple of 4. And this is actually going to be a key point that we'll discuss later. So now I'm going to document a simple approach on how you could theoretically tackle this problem. But we're going to find out very quickly that not only is this method inefficient, but it may be truly impossible to code as is in any language you choose. So if we take some value of n, how can we figure out all of the pairs of a and b such that n can be represented as the sum of two squares, or this equation has solutions? So the most naive thing we can do is try every possibility. So we can consider some value of n, and we can cycle through every value of a. We can use this formula, since we know n, and we're cycling through different values of a, to determine what b must be. Using this formula, we can check, is b an integer? If b is an integer, and a already was an integer, that means that a squared plus b squared equals n, or that the value of a and b we're looking at satisfy this equation. We can cycle through every possible value of a, so we'll increment a by 1, change b accordingly, and keep looping until eventually a is greater than b. We do this because we already had the stipulation that a must be less than b. So once a grows greater than b, we can stop checking. So theoretically, running this loop and checking every single time if b is an integer, we can find every single pair of a and b that satisfy this equation. But there's one major problem. What values of n are we considering? Now, if you'll remember, we are doing this for all n that are square-free and only divisible by the primes that we already talked about. So the largest possible number that we might consider is the product of all of the primes that take the desired form and are less than 150, like was on the previous board. So n max would be this product, 5 times 13 times 17, all the way up through all the primes up until 149. And that product is roughly 2.5 times 10 to the 27, something like some sextillion or even larger number. And none of the data types in MATLAB, in Java, anything you might use, will accurately be able to support that number. Because consider, not only do we need to know what this number is, but then we're going to subtract things from it, and we're going to take a square root of it. And working with numbers that large, performing those operations just does not produce accurate results. Additionally, say we did get accurate results through doing the subtraction in square root. This code would take forever to complete, because for any n, the number of a values that we might have to check is the square root of n divided by 2. You can confirm that using some algebra, moving around this equation, since you know that the largest value of a is when a and b are equal. And you will still have to check billions of different values of a if you want to find every value of a and b such that n is represented as the sum of two squares. What we're about to see on the next board is that there's a beautiful formula that we can use that will simplify this problem incredibly, so that we don't need to do the calculations of checking every single a and b, but actually there's a beautiful trick that we don't need to check any a and b's, but we can actually determine what a and b are using a nice pattern.